Hey everyone, and welcome to this explainer. Today we're diving into the absolute foundational building blocks of all modern electronic circuits, transistors. We're going to take what usually feels like some pretty dense, dry textbook theory and completely break it down. By the end of this, you'll see exactly how these tiny, unassuming devices actually control the entire electronic world around us.
But first, I want you to think about something. How in the world do three simple connections dictate the behavior of practically every modern electronic device? It's honestly fascinating. Just by swapping which wire connects to which pin, you can fundamentally change a component's entire set of capabilities, literally transforming it from a smooth signal booster into a hard, fast digital switch.
So here's our game plan for today. We'll start with the 3 ways to connect a transistor, move into the magic of amplification, check out the input and output characteristics, and then compare all these setups side by side. After that, we'll track down the operating point and finally unpack the cutoff, active, and saturation states. Let's get into it. Section 1, 3 ways to connect. Let's talk about the 3-lead dilemma. You know, every engineering marvel usually starts by having to solve a really basic physical problem. The transistor is no different. Physically, transistors only have 3 leads: the emitter, the base, and the collector. But here's the catch. Standard circuits actually require 4 terminals. We need 2 for an input signal and 2 to pull the output signal. So what's the clever engineering workaround here? Well, we just make one of those transistor leads do double duty. We use it as a shared common terminal for both the input and the output. And because there are 3 leads, that gives us 3 distinct ways to wire the whole thing up.
In our first configuration, called the common base, check out the looping input path, feeding the signal right between the emitter and the base. Then, on the other side, the output path is taken between the collector and that same base. The base sits right there in the middle, grounded, and shared perfectly by both sides of the circuit.
Now contrast that with our second setup, the super popular common emitter. Here, the emitter becomes our shared foundation at the bottom. Our input signal is applied between the base and the emitter, and then that newly amplified output is harvested from the collector and the emitter. Rounding out our trio, we have the common collector connection. And yeah, as you probably guessed, the collector is now the shared terminal. The input goes straight into the base, but the output is uniquely pulled from between the emitter and the collector. It's wild to think that simply by rotating which pin access our ground floor, we completely change how current flows through the device. Moving on to section 2, the magic of amplification. Let's look at current and voltage gain. Okay, now that we know how to plug them in, let's talk a little bit of math. But don't worry, we'll keep it grounded. First up is alpha. Alpha is the current amplification factor specifically for that common base connection. Think of it as the ratio of the output collector current to the input emitter current. But there's a slight catch here. Because a tiny fraction of the current is always lost to the base, the total collector current can never quite equal the emitter current. So alpha is always going to be just under 1, typically ranging from 0.9 to 0.99 in your standard commercial transistors. Next up is beta, and this is where things get genuinely exciting. Beta is the amplification factor for the common emitter connection, measuring the change in the output collector current relative to the input base current. Because less than 5% of the emitter current actually flows into the base, when you divide the collector current by that tiny base current, you get massive gains. We're talking anywhere from 20 to 500. This huge current and voltage gain is exactly why the common emitter is basically the undisputed heavyweight champion of electronics. And to finish off our Greek alphabet, gamma completes our toolkit for the common collector connection. This one is the ratio of the change in emitter current to the change in base current. It gives us a current gain that's pretty comparable to the common emitter configuration, tying all our math right back into the actual physical flow of the circuit.
Section 3, transistor input and output characteristics.
So formulas are great and all, but let's visualize what actually happens when we put these setups under pressure. If we look at the common base, the input curve is incredibly steep. What that tells us is that just a tiny increase in voltage causes the current to absolutely shoot up, meaning the input resistance is very small, literally just a few ohms. But look at the output curve. It's almost perfectly horizontal. Once you get past about 1 volt, the collector current flatlines. It becomes highly resistant to voltage changes. It depends almost entirely on the input emitter current, making the output resistance incredibly high. Section 4, comparing transistor configurations. Let's look at them side by side. We've seen the setups, we've done the math, and we've checked the graphs. So let's pull it all together into the ultimate cheat sheet. Notice the real-world applications here.
Because the common base operates so well with low input resistance, it's your go-to for high-frequency applications. Meanwhile, the common emitter gives us both high voltage gain and high current gain, making it absolutely perfect for audio frequency stuff. And the common collector? Well, with its super high input resistance and low output resistance, it doesn't really amplify voltage at all. But it is an absolute champion at impedance matching, smoothly bridging a high resistance source to a low resistance load.
Section 5, finding the operating point, also known as the cue point.
Now, before a transistor can amplify a dynamic, changing signal, like your voice on a microphone or your favorite song, we have to establish a baseline. This brings us to the cue point, or quiescent point. I want you to think of this as the perfect, silent resting state for our circuit. It's located exactly where the DC load line intersects our target base current curve. That specific coordinate tells us exactly what the zero signal values are. It's essentially the transistor waiting silently, perfectly biased, and completely ready to spring into action the split second an active signal hits it.
Section 6, cutoff, active, and saturation, the operating regions.
Okay, now for the highly practical payoff. What actually happens when we push this component to its physical limits in a live circuit? Well, a transistor operates in 3 specific regions. An easy way to frame these 3 states is using a water valve metaphor. Cutoff is when the valve is fully 100% closed. Active is when the valve is carefully adjusted to control a very exact flow. And saturation, that's when the valve is blown wide open. If we look at the 2 absolute extremes of our load line, we find our physical limits. Down at the bottom right, the cutoff state is the point where the base current drops completely to zero, nobody's home. Up at the top left, we have the saturation state. That's where we hit maximum collector current and the voltage drops practically to zero. But right between those 2 extremes lies the active region. This is the Goldilocks zone, the crucial sweet spot. In this region, the emitter diode is kept on, meaning it's forward biased, and the collector diode is kept off, so it's reverse biased. Maintaining this delicate balance is exactly where normal transistor action and linear amplification actually happen. So here's the big conceptual leap you need to take away from this. When the transistor is in that active state, it carefully scales your signal. It's acting as an amplifier. But when you slam it into cutoff or saturation, that normal transistor action is totally lost. It stops tuning the signal and instead acts as a hard binary gate. It becomes a simple open or closed switch. And these theoretical regions translate into stark physical realities for the circuit. In the active state, it's a working amplifier. In cutoff, the pathway between the collector and the emitter is completely open. No current flows whatsoever, literally just like a light switch flipped off. In saturation, it effectively shorts the collector and emitter together, acting as a closed switch, allowing maximum current to just pour right through. We have covered some deep foundational concepts today, from common emitters to cue points to saturation states. But I want to leave you with one final thought. Take a look at the device you're using right now to watch this explainer. Whether it's a smartphone or a laptop, its processor relies entirely on these states. Think about how many billions of these microscopic transistors are sitting on that tiny silicon chip right now, actively toggling between cutoff and saturation, opening and closing billions of times a second, just to render this video on your screen. It is absolutely incredible when you realize that all of modern computing is just this textbook theory, brought to life on a microscopic scale. Thanks for joining me today, and keep exploring.